Welcome to the Polymer Science Podcast. I am Dr. Alicia.
And I'm Jacob Shackman.
In this podcast, we'll be speaking to researchers from around the world and talk to them about how their work is improving our daily lives. I hope you enjoy our conversation and that you learn something new. Hello everyone. Today we are talking to Gregory Parisi. He is a PhD student at Rensselaer Polytechnic Institute and worked at the AGH-UST Faculty of Metals Engineering and Industrial Computer Science with a previous guest on our show, Urszula Stachewicz. He also won an award for the second best poster at the ESEE conference this year in 2023. His topic was called Photoresponsive Electrospun Fiber Meshes with Switchable Wettability for Effective Water Harvesting in Variable Humidity Conditions. So we'll be speaking more about that topic specifically, with the focus being on electrospinning and also the type of materials that he was using for the fog water collections. Thank you for listening. I hope you have a nice time listening to this episode. Please let us know what you think, and you can also share this if you enjoyed it. Welcome to the Polymer Science Podcast, Gregory Parisi. It's so great to have you on this episode. You are working as a student currently. You even had an award recently won for second best poster at a conference. I just want to get more into what you're currently doing, and if you can just introduce yourself to the listeners and tell us a bit more about yourself, that would be great.
Yeah, certainly. It'd be my pleasure. Thanks for inviting me to speak on this podcast. As you mentioned, I'm a PhD candidate. I'm actually a candidate in mechanical engineering at Rensselaer Polytechnic Institute in Troy, New York. I've been conducting research in the field of mechanical engineering, specifically on interfacial phenomena and switchable surfaces. I'm sure we'll get into that more because that's kind of what the research I'm doing now is about. But currently I'm a Fulbright fellowship in Krakow, Poland, so I'm not in New York. I haven't been there since last October, and I'm working in the electrospun fibers group under the mentorship of Professor Urszula Stachewicz. And I'm mostly studying fog water harvesting here in Poland.
Awesome. Well, congratulations just firstly on winning that second prize for the poster. This was at the 6th European Symposium on Electrohydrodynamic, Atomization and Electrospinning this year, conference. Just tell me briefly, how was that experience for you?
Yeah, sure. And yeah, I know a lot of these conferences have really long names that are definitely a mouthful, but
the ESEE, or what is it called?
Yeah, exactly. You need the acronym to get through it. But yeah, it was an honor to win the prize. And to be honest, it was just a lot of fun presenting and showcasing the research I was working on. The symposium in general was a fantastic experience. It was my first international conference, so I got hands-on experience with that. And yeah, it was a lot of fun to engage with researchers from all over the globe and to be able to exchange ideas, learn about groundbreaking studies on topics that I'm not completely familiar with, since my background's actually mechanical engineering, not electrospinning and polymer science.
Okay.
But so I was able to learn a lot and engage with a lot of wonderful people. And also was in Krakow, which is a city I've really grown to love. It's a great place and it's a lot of fun.
That's awesome. Yeah, so the poster that you got the award for was called Photoresponsive Electrospun PVDF Titanium Oxide Fibers and Meshes with Switchable Wettability for Fog Water Harvesting. Also a mouthful.
Yes.
But for the listeners that maybe do not know, could you just tell us a bit more about the material that you work with, the PVDF Titanium Oxide, and how it was prepared and basically what you were doing with it?
Sure. So PVDF is a polymer, polyvinylidene fluoride, and I incorporated titanium dioxide nanoparticles into these fibers. These fibers were prepared with an electrospinning process. Basically, I got very, very small fibers of PVDF where it was had TiO2 nanoparticles embedded all throughout the fibers. Yeah, that's basically the only
Awesome.
polymer that was used in this setup.
Great. So when you like selecting the material, what is the criteria that you usually look for, especially with the regards to this application that the material was being used for?
Right. So the most important and like a necessary selection for the polymer, it needs to be able to form a solution or a melt of some sort to produce consistent or uniform nanofibers. So with that, the electrospinning process wouldn't be able to start at all. So in order for these solutions to be made, they need to be soluble in some sort of solvent or water-based system. So looking past these two important deciding factors, I would say the most sought out properties of materials need to be that the polymers need to possess strong mechanical strength. And in other fields, they might possibly need to be biocompatible or thermally stable, biodegradable. But you kind of pick and choose what you want depending on the application. So for the application of fog water capture or fog water harvesting, I want a material that's mechanically strong and has the appropriate chemical surface chemistry that I'm looking for to capture water and release it quickly.
Awesome. Yeah, so that is actually we can actually get into. I want you to talk a bit more about the fog water harvesting as well. But before we mention that, you actually mentioned it very quickly in the beginning of the episode that you were working under Urszula Stachewicz. Is this currently a project that you're still doing with her, or are you done with the collaboration that you were doing in Poland with her?
Yeah, the collaboration's still ongoing.
Okay.
We've actually started a second project, so a little bit different than the PVD-FTIO2 project, but we're continuing on with water harvesting, and I'm working with her and her group, which has been an amazing experience.
Awesome.
It's been the best thing about the Fulbright experience is the group that I decided to join.
That's great to know. Did you know that she was also a guest on this podcast?
I did, yes. I've listened to that episode as well. So
that's great. Yeah, so that was also a topic that we spoke about, but I think it's always great to just maybe get into it in a bit more detail. Especially like, could you just explain like the electrospinning process before we get into a bit more of the technicalities of it? So in case the listeners that do not know exactly what electrospinning is, just they can be also part of the understanding of how it works and what the mechanism is surrounding electrospinning itself.
Yeah, sure. I could definitely try my best to explain electrospinning. But it's basically a method that produces fibers using electrical forces. So using these high electrical forces, it stretches charged polymer solution out from a source in most cases. And in the case that I was using, it stretches the polymer solution out of a needle. So as the electrical field strength increases, this polymer jet it's formed and the jet itself undergoes elongation until it gets drawn and kind of placed onto a collector. So it's during this process that the solvent in the solution evaporates and all you have left is fibrous polymer.
Awesome. Yes, that's usually why the importance of the parameters selecting the material is also quite crucial. Otherwise, like you mentioned, you won't be able to get that cone effect and then the electrostatic part of it as well. The conductive part of the solution needs to be there as well.
Yes, exactly.
So when you went ahead and selected the material that you were working on for the fog water collector, was there other parameters that you needed to take into account, or was it just the durability? Was there any consideration for the consumable, the recyclability of it as well, or reusability or anything like that with regards to cost efficiency, anything like that as well? Or
yes, that definitely had a large play in it because since I'm doing water harvesting, this would be, in real application, it would be used outdoors. So I'd want something to be reusable, mechanically strong, and durable because it needs to be used 24 hours a day, day in, day out, as long as it possibly could. So yeah, some of the parameters and the processes that I had to set up was, as we already spoke about, the solution preparation concentrations. But also in my case, a big factor was the concentration of the titanium dioxide particles.
Oh, yes.
So I wanted to incorporate as much as possible without compromising the fiber morphology or, compromising a homogeneous fiber structure.
Oh, that's true. So, what role did the titanium dioxide play in the efficiency of the whole product as a whole?
So the point of the titanium dioxide was to incorporate a particle that could switch the wettability of the surface. So the more titanium dioxide that was on the surface of these fibers, the quicker that this switch could happen. The issue is when I started incorporating too much TiO2 into the polymer solution, then problems would arise in the electrospinning process itself. Either agglomerations would form or there would be clogging issues. So there was like a careful balance that needed to be met in order to get a lot of TiO2 and also for the electrospinning process to be complete.
To actually work. Yeah,
exactly.
That's usually the biggest problem. So if you try to like incorporate too much of a certain particle, then there's either agglomeration or just electrospraying. No more fiber.
Right. Yeah. And you could even go further than that and not have fibers or spray and just have a mess on the collector.
A congealed mess.
Exactly.
Oh my goodness. So you've mentioned now the switchable wettability, that term. Just in case there's anyone that doesn't understand quite exactly what switchable wettability means, can you break that down for me a bit more and explain what exactly you mean by if you say switchable wettability of a fiber or of a fog water collector?
Yeah, sure. So this is actually like what I was studying for majority of my PhD before focusing on fog water collection in Krakow, but I guess I should start with what wettability is. And it's really just the liquid interaction of fluids and solids defined by this contact angle, which is the contact point between the liquid vapor interface and where it meets the solid liquid interface. So you could have two extreme cases. You have the extreme wetting case, which I like to think of a droplet touching a paper towel where it completely wets the paper towel, and you would have a contact angle of 0, or you would have the complete non-wetting surface, something like adding a droplet to a Teflon non-sticking cooking pan. So to have a switchable wettability surface, you would need to, it's basically a surface transition between these two extreme wetting states that I just mentioned. And in a theoretically perfect situation, you would want to switch between a spherical droplet and a droplet that completely wets. And of course, there's tons of different ways to switch it and different external stimulus that could be added to get different effects.
So this switchability is quite crucial when you're working at areas or environments or even climates that have a variable humidity, like the conditions are not always the same. So is this what this that property is for, right? The characteristic of the mesh needs to be switchable because it needs to be adaptable.
Exactly. And actually some external stimulus to get a switching property is these external environmental factors. They're called passive switching, like you mentioned, humidity or temperature. So without any external interaction, you can get this natural switching phenomena on a surface just by this external stimulus. So in my case, yeah, I chose PVDF because it's very hydrophobic. And incorporating the TiO2, we could switch the TiO2 nanoparticles to hydrophilic. So you're getting this switch from a hydrophobic surface to a hydrophilic surface.
I see. What is the external stimulus that you're talking about?
In my case, it's UV light. So titanium dioxide, it's a photocatalyst, and it goes through something known as photoinduced hydrophilicity. So when it's exposed to UV irradiation, it creates these surface oxygen vacancies. and
see.
the entire surface would then be populated with hydroxyl groups, which are very polar and attract water. And so now the water droplets no longer see the nonpolar PVDF, they see this very polar hydrophilic TiO2 surface.
And then when you switch it back, how does that happen?
Yeah, so switching back, that's always like a crucial but very difficult part to achieve, and it's not always possible depending on the surface and the properties, but in my case it is possible, and I knew that before choosing TiO2 because it does have this effect. But when the TiO2 is completely dehydrated, it removes all these hydroxyl groups. So basically when it gets warm enough and the water evaporates, it goes back to the hydrophobic state. So in principle, UV light and heat are both things that you could find just keeping this mat or this mesh outdoors for external switching, or possibly dynamically switching it on demand.
That's amazing. That's awesome. Wow. So have you tested this out in like the field?
No, unfortunately not. And yeah, like as I mentioned, I've only been working on electrospinning, fog water harvesting since I've been in Poland, which has been since October. And although like the
fresh.
right. And yeah, I wish I had more time, but my fellowship's coming to an end. So it was not enough time to do field research, but I would love to, because some of the areas that have these high fog conditions in arid regions are definitely places I'd love to visit.
Yes. Like I was only thinking like in Africa and like where there's like a lack of water or fresh water. I mean, that would be such a great feature because it's like almost like a waste of water. You know, the water that's running down the side of the house can actually be collected in some ways. So that's actually now very interesting to see.
Yeah, and I think this is like a lot of these ideas come exactly from that. Because yeah, in southern Africa, there's the Namib desert beetle, which is like condenses the water on its shell and is able to kind of direct water into its mouth, or how it drinks the water.
That's so interesting.
And
that's almost like so you're taking some inspiration from the nature as well.
Yeah, of course it's not me that took the inspiration. This is an old concept called biomimicry, where researchers copy insects, or even like the redwoods in California. This is probably more relatable to my application because they have these needle-like leaves and branches that can catch fog in the air, and it runs the water down to the roots.
Wow, that's awesome. Yeah, it's actually like that biomimicking term keeps popping up every time I do polymer science research. It's like almost like a nice way of reminding us not to reinvent the wheel. It's already been done. Nature is good at it.
Right, it's the best at it, so just copy that.
Exactly. So in terms of other types of, if there's like other types of material being used for fog water collecting, how does this compare to those? Do you know?
Generally, yes. Like, so I mentioned I didn't do any field studies on my mesh, physical. So it's tough to compare lab to lab kind of results. And of course, fog water harvesting, it's not a new technology. This has been something that's been done for centuries in parts of the world like Peru and like these foggy arid environments or cloud forests. So the idea is not new, but just inventing ways to improve the efficiency and to use it in areas that don't get as much fog as I think areas that could be improved.
That's true.
But even in applications today, you can, and depending on environmental conditions, you get meshes that collect maybe on the low 2, 3, 4 liters per day to several hundred liters per day. And with several hundred liters per day, we're talking about, huge dozens of meters long and high meshes or towers. I've seen like more original constructions and fancier constructions of these meshes that can collect several hundred liters per day.
Yeah,
but I, of course, was using it on the lab scale. So using it in centimeters size, so converting it or assuming that it could be converted to meters squared we're talking maybe like 2 to 10 liters per hour per meter squared.
Yes. Wow.
So it's still an appreciable amount. But
Yeah, it is.
this is in a controlled environment,
That's true. Yeah.
not in the field.
That is usually, yeah, that's also always the most frustrating thing, is like having to upscale something. So it works here, but does it, like, can you expand it and turn it into something massive, or reproduce it in like an outer exterior situation? But
Right. And
that's where the selection of the materials and everything is crucial. You focused on that part. So
yeah, especially in this field, because most of the areas that need this type of sustainable water source are in more poor areas of the world that a lot of funding is not going to be used to make these very expensive meshes. And so yeah, it's pretty important as well to minimize costs and also improve the way that the meshes could be taken care of, because you don't want to spend thousands of dollars to maintain something that doesn't really cost much.
That's true. That actually makes a lot of sense. Yeah. So if you're testing the fog water collector, do you place it into like a humidifier type of chamber, or how do you test these materials?
Yeah, we have them in a controlled environment, pretty much just a large acrylic box that has controlled temperature, and we have a stream path of fog that flows from outside of the chamber inside the chamber through the electrospun mesh. And we have a gutter system under the mesh that then collects the water, runs it back outside of the acrylic chamber and onto a balance where we can actually do
the measurements and so on.
Measurement by mass, exactly, instead of volume.
That's amazing.
So none of that is affected by the conditions within the chamber, and conditions like temperature and, more importantly, humidity.
Yes. Yeah, that's true. I think in terms of the only complications but you maybe have an answer for this, but in terms of complications that I've seen, if you kind of collect the water in a hot, humid environment, and you're trying to like store that water, but the water maybe evaporates as fast as it's collecting sometimes.
Yeah, that definitely could be an issue in hot environments. Yes. I think it would be even worse if it was a non-humid environment and hot.
Oh, yes. But I just want to quickly talk about some more of your current work, and if there's anything that you're currently going into more and focusing on with your research. Can you just share us a bit more about your upcoming projects, or any interesting events, or something that you're currently passionate about that you can share with the listeners?
Yeah, I would love to. In terms of research, we're trying to change actually the geometry of these electrospun fibers. So there's other research out there that have used mostly steel harps, essentially, to collect water out of a fog stream. And the point of that is that you don't have any of the droplets being impeded by horizontal fibers. So in theory, if we have all the fibers going a single direction, the water droplets should drop down quicker. So in this new project, we're still using PVDF, but are making yarns out of it. And from these yarns, we're harping them onto a collection device that could more efficiently collect this water. So that's one of the projects, and I'm hoping to finish that within the next month or so, because that's when I go back to New York. And yeah, my last project would be trying to write my dissertation and finish up my PhD in the next year. So that'll be much. But yeah, I'm kind of sad to be leaving Poland because it's a great country, but also excited to move back to New York. I actually recently got married right before coming to Poland. So thank you. So I'd love to go back to New York and actually be with my wife.
Yes, for sure. Oh, well, congratulations with that. No, it sounds like you have a lot on your plate, but it's all good things and exciting things. So really good luck with the rest of your endeavors and the projects that you grab. I hope that they'll be successful, and congratulations on being married and, and also finishing up the thesis and getting that PhD. It's going to be an exciting path ahead for you, I'm sure.
Yeah, exciting, busy, but it's all very good stuff. And
and research, just in general, the type of field you are in feels like it's never ending. Water research and environmental, like just trying to improve the people's daily lives by getting them to have a better water supply, and all those types of projects that kind of gives back to the people. I feel like that's always something that you can be passionate about and stay passionate about, and grow with the technology. And it's just nice. I think you're in a really good field for developing with the polymer science part of it. So it's awesome.
Yes, I agree. And it's easy to be passionate about it when it's such an important issue. Like all the time I just read about, this global issue of sustainable water and how there's like projections of water not being enough for the growing population and everything like that. So I think it's an important topic, and finding new ways like electrospinning to capture water in areas that are not close to maybe water is important.
That's true. No, that's really amazing. I find this topic very fascinating, and like it's inspiring because once again, it's like polymers are being utilized for things that we kind of underestimate. So it's awesome to hear how you and your project has been progressing and adding to this field. So thank you very much. Is there anything else that you would like to share with the listeners? Maybe, where they can find you on social media, or if they want to read more about fog water collectors, anything like that. You're welcome to share any links with me, and I'll put them in the show notes.
Yeah, definitely. I could share the link to the electrospun fibers group, as I mentioned, with Professor Urszula Stachewicz.
That would be great.
They could find a lot of research that the group has done well before me on water harvesting.
Awesome. I'll do that. Thank you.
Yeah, thank you so much.
Awesome. Thank you so much, Gregory, for the time and just chatting to me about this awesome project. It was really great to talk to you.
Yeah, it was really great to talk to you as well.